last year these two were not on the test, the AP exam. This year they are. The fair game.
The limit and the root.
Yeah, these were previously not on the AP exam, but now they are. The root nest. Something wasn't me. Okay, so all of this is fair game for the exam. Many of the, like if you get a free response, most of the time you can solve it with a couple of different tests, right? So you're going to know all these. We're going to write cards for them. You're going to have them memorized, right? You're going to study those. So you are going to try not to do or do not. That is the truth. That would be Yoda. The quote, Yoda.
Yeah.
Okay, so we're on our last two tests today. How's that sound? Yeah? Okay. They all have their specific uses. Today we'll start. I'll start giving you commentary. Don't say use the ratio test. Here's the ratio test. Okay, well, there's the key right there. We're going to use a ratio. It's going to determine convergence of attributes. So,
is it going to be simple like 2 to 1 or something like that?
yeah, basically you're going to use a limit here, and it's going to give you an answer that's going to tell you the convergence or divergence. But you have to do one thing first. Your book uses P. So it's another one of these infinite limit tests. Here's the ratio. Okay. So the limit has to exist, obviously. This is going to be the series as it's written, and this is going to be the series plus 1 term. Right? So you have to figure out the plus 1 term, put them in a fraction, calculate the limit. If P is less than 1, what happens to the series?
If it's less than 1.
Think about what's happening here.
Oh, because it's absolute value.
If it's less than 1, the bottom is bigger, right? So that means the nth term is bigger than the next term. So it's decreasing, right? So this converges. And not only converges, but it converges absolutely. Okay, which also means that it converges, right? Okay. Remember that. What if P is greater than 1? Yeah. No. It diverges. No. The only time we worry about convergence, absolute convergence, or conditional is convergence. But, so you think about this, P is greater than 1, so that means the top is bigger, right? Which means each successive term is getting bigger. The series is going up. Okay. Last situation. If P is 1. The test is inconclusive.
You have to use, if you get one, but you have to get more terms to see what happens here.
If P is 1, you cannot use the ratio test at all. You have to use something else. Alright, so use a different test. Right. Don't do nothing. Bummer. All that work and then nothing. Right? Okay, this one is really useful. That with factorials. If you see a series with a factorial in it, this is the one you probably want to use. Good. Well, you want to look at the trigonometric identities. Yeah. So if you see a factorial, this one is really, really useful. Okay. So let's look at one. Does this converge or diverge? Or prove? The book says prove that this series converges. You can ask it many different ways, right? It?
The series is greater than one, you could.
Let's define it again. I'm sorry, we're just having fun. Because math is fun. See, you guys laugh at that?
No, it's more along the lines of I made a fun.
You're becoming math nerds. I'm just gonna throw it out there. I'm getting to you. Okay. What are you saying, Hunter?
Well, if n is the first term, it would be 2 over 1. So it's greater than 1. So the series is greater than, P is greater than 1. So
Okay, you haven't done hardly any of the work yet. Okay. First of all, we have to have the n plus first term and the nth term. So we need a to the n plus 1. Right? That's where you put n plus 1 in here. So 2 to the n plus 1 over n plus 1 factorial. Okay. You think? Because the book says prove that it converges.
Because factorial thing, after it gets to like a certain point, it just explodes.
A sub n is still 2 to the n over n factorial, right? Okay, so we need the limit as n approaches infinity of 2 to the n plus 1, n plus 1 factorial over 2 to the n over n factorial.
it's 1/2.
What is?
The series is 1/2 n plus 1. The original is 1/2. It's 1 over 2. Because the first one, the newest one, the newest term is 2 things.
Okay, let's check your assertion. If you can do that in your head, you got me beat.
No.
Okay, fraction, fraction division, right? You guys should be really good at this by now. Copy, dot, and then flip. We use it all the time, don't we?
Oh, so we would not just solve them and
No.
then put them over each other?
You want to algebraically simplify this so that you can solve the limit easier. This is why I was trying to follow your line of thinking. It just wasn't happening 10 steps down the road, so we could work it out. Okay. Always carry your limit. Okay, this here is 2 to the n and 2 to the first. Remember that property of powers? This here. if these two are added, it means you can split with the same base and multiply. Okay. N plus 1 factorial is n factorial times n plus 1. Because remember, let's say n plus 1 factorial is n plus 1 times n minus 1 times n minus 2 and forever on, right? This here can be written as n factorial still, right? While we split this apart because we have an n factorial up here. If we have one on the bottom, we can cancel them out, right? So, and leave these the same. Right, so you're using your properties of factorials and powers to get rid of stuff. Okay. What can we do? Right, now we have the limit as n approaches infinity of 2 over n plus 1, which is 0, right? And then since the bottom is infinite, the top is 2. It's the limit. All it is. So since the limit of the ratios equals 0, which is less than 1, right? The ratio test is less than 1. The series from n equals 1 to infinity of 2 to the n over n factorial converges. Okay. So the real trick here is to get that simplified properly. Yeah. Here's another one in your book if you want to look at it. N squared over 2 to the n. And there's also an alternating series in there. And then there's also one where it shows that it's equal to 6. You want to see those one. Okay, I'm fine. Okay, let's look at this series. I bet they can't hear him very easily. They could probably still hear him really loud. I would also note this works well on factorials and exponentials. Right? Like 2 to the n. So this would be n factorial, that would be 2 to the n. So kind of keep that in mind. We have both for this problem. But we also have an alternating series, right? Is that going to matter?
So you
don't have to worry about this because we're doing all absolute value. Okay, so what's a to the n plus 1? N plus 1 factorial. And you don't even have to write these down now if you don't want to. I just did it to point it out to you the first time. And we know what a to the n is, right? A sub n. So Some people get good enough they can just write it, copied off of it. You okay with that? So instead of dividing them and then rewriting it as copied off of it, and yada yada yada, just write it out right now. Okay, so this is the limit as n approaches infinity. What are we going to cancel out? An n factorial, right? What's left? N plus 1. And what are we going to cancel out here? 1,000 to the n. What's left over? 1,000 on the bottom, right? And that is infinity. So, write your statement. Since the limit as n approaches infinity, series notice the factorial is on the top there. That's the kicker. Usually factorials increase a lot faster than exponentials. Yeah. They kick you in the face there. So, I mean, if you know you have to use a ratio test, it's really difficult. So, figuring out which test to use is a trick. Right? The root test is very nice, especially when we have roots. Okay, so the root test. Assume the limit exists. That limit exists. It's absolute value. Alright, so we just called it L this time to distinguish it from the ratio test. Okay, L is less than 1, what happens? Yep. What does? Yeah. Okay, good. Oh. I said less than, didn't I? Yep. If L is greater than 1, series diverges, it's the same conclusion as the ratio test. And what if the L is 1? Yep, and conclusive. Okay, so again, just another test. Just gotta set it up. Obviously, it's going to be very useful with nth roots. Okay, that's the example I'm going to show you as an nth root, or an exponential. That's good grasshopper. Good point. does this series. Converge or diverge? Notice it's an exponential, right? So this would be an awful one to use a ratio test on because you'd have n plus 1, n plus 1, n plus 1. Not very easy to cancel out, right? So I would tend to the root test because we're doing the nth root of an nth exponential. It's going to really just fall right apart. So well, the limit as n approaches infinity, nth root. Do we need the absolute value here? You can write it, but you don't need it because everything's positive anyways, right? If n is 1, 2, 3, everything's positive. So we can just kind of, but what's the nth root of an n exponential? Yeah, it's just n over 2n plus 3, which is so series. Converges. Right? That's it. Ratio limit tests. All our tests are done. Yay! You just have to know how to use what? Liar. I'm not a liar. What other tests do we have to do then?
Then if you are not a liar, you'll have no test.
No, all the series tests are done. Except when I give you a series exam next week.
So you're still lying.
No.
Make up your mind.
Here's the ratio test problems. And then some root test problems. And again, pay attention to what type of functions those are: exponentials, roots, factorials. Identify items that can help you lead that way. And then here's where you get to start picking any test: 43, 49, and 51. All right, spiral. That was mean. You guys don't have a lot going on today. No, we're not. I said I hope, doesn't mean it's actually. There you go. But you still have 10 minutes, so you can get a couple minutes. So the rest of this chapter is power series and Taylor series, where we look at you know what a Taylor series is, a Taylor polynomial made into a series. But those are all 2-dayers, both 2-day lessons. There you go.